This last two videos, we're gonna end the pre-processing by talking about what is called shift correction or warping or aligning, which incorporates a lot of different methods, but we're mainly gonna focus on one, namely what is called correlation optimized warping. And the idea that we pursue is that sometimes we have data where there's a lot of shift going on. So the peaks, for example, that should come out at maybe around 1900, they come out at varying positions at various time points. Here we have chromatographic data, but it could also be spectra and other things. And our normal models don't handle that so well. So if we could somehow align our data so that the peaks came out at the same time point, that would probably help us improve our models. And I'll show you in which way that would help. Well, first of all, the models that we usually use are kind of bilinear or linear, depending on how you look at it. Methods like PCA, even neural networks, normal traditional feed-forward neural networks, PLS models, etc. They assume that the features that are used appear in the same position always. That's the meaning of the word bilinear. So for example, in this example here, we have the same peak in various concentrations, but the shape remains the same. That's basically Beer's law. Now you can see how you can model that with a one-component model. Imagine that the same peak was measured several times, but at different positions. Then there's no way you can model that with a rank 1 system. You need at least 3 components in this case to model the data, one for each of the shapes. So you can maybe see that using a bilinear model here will lead to complicated models. You need more components, more parameters. So if you can avoid this, you get simpler models essentially. And one way of trying to align such data by pre-processing is what is called correlation optimized warping. And correlation optimized warping tries to take two signals. So assume we have a green target signal and we would like all our additional signals, like the blue sample, to have features in the same positions as in the green one. It's symbolized with a little train below. But the idea anyway is that we look at the signal in different segments, like this. And we try to stretch the time points. We basically interpolate the time vector in such a way that the data better aligns. So you can see if I would call this time 1 to 10 and I call this time 1 to 10 and then interpolate my data appropriately, well then I actually have aligned my data. And that's basically the idea in correlation optimized warping, or COW. And the goodness is measured by how well the two signals correlate to each other. You can see that if we align these two signals here, they would have a higher correlation than the raw data, because for example in this position here the correlation is 0, but if they were aligned like this, well then the correlation would be much higher. So the good thing about the correlation optimized warping is that it's fairly good at preserving shape. So that means the peaks do not necessarily change their form or shape while aligning, and that's an important thing. If you take it to the extreme though, the shape will change. COW is used very much for example, chromatographic data or NMR data, and also in many other situations. So let me show you what you can achieve by doing cow alignment. So here we have a small data set, some peaks, and you can see that they are misaligned. But once we warp the signals, we get a fairly perfect alignment. And let me show you why this is useful. Well, if you take a look here, if I do a PCA on the raw chromatograms on the peak, or let me show you, wait a minute, here, if I do a PCA here and I do a PCA after alignment, well, you will notice some differences. You may think that they look kind of similar, but if you look at the variance explained, you can see that in the aligned data, I get everything explained more or less in the first component, whereas in the unaligned data, I need much more components because the peaks are changing. We're trying to model this peak here. It makes sense that after alignment, we can describe the data more easily with less components. So that's perfectly fine. Another thing is that in the unaligned data, the first component, this one, it's sort of the envelope of all the peaks. So it's going to be wider than the actual peaks. It does look like a peak quite naturally, but it's actually wider than any of the peaks because it's describing sort of all of the peaks at one. So that's why the components are wider when we have not aligned the data. And finally, one thing you will notice is that the first component has the shape of a peak, even though it's a wide one. The second component looks like the derivative of the blue one. And actually the third one looks like the derivative of the second one. And this is a very good indication of shifts, because you can actually model shifts by an overall shape plus a derivative. You can verify that in MATLAB if you are skilled and see that indeed you can model shifts like that. So every time you see something that looks like an overall shape and then a derivative, that would be an indication that we have shifts in the data, and that alignment may be a good idea. Okay, we can do alignment in PLS Toolbox, for example. You can also find algorithms available online for doing CAL. There are many of those, but it's available under variable alignment, and we will try that. Unfortunately, we cannot do CAL on freeway data. So, for example, if you have GCMS, so that would mean you have many samples, you have masses, and you have time. You can't actually do CAL in this particular implementation, but in the next video I'm going to show you how you can do that, at least in a fairly reasonable way anyway, if you have, for example, GCMS data or LCMS data, something like that. Okay. So there are two parameters that we need to, well, maybe actually three. There's the slack, the segment, and the target sample. And the segment is simply the length of each interval. And the wider you make that segment, so let's say I only do 2 segments, then you have very little flexibility, and there's very little you can change. So you can only handle very minor shifts. If on the other hand I make the segments extremely narrow, then I can basically align to almost everything, and I may even end up with my data just in one line, so to speak, which is perfectly aligned but not very meaningful. So we have to find a compromise. We have to find a segment that will do fairly well on our data without destroying the shape. And for that we define the segment, but we also define how much the segments can sort of move freely. That's the slack. How much am I allowed to stretch a segment? And again, the more I can stretch it, the more I can adjust my signals. And these are these parameters are fairly important, so you typically have to sit and play around with those quite a bit. You can use some intuition, but you have to typically play around a little bit. Now you may wonder if we couldn't automate this, and actually we can. I'll show you how to do it in the next video. Unfortunately, it's not so very user-friendly, but we can automatically find reasonable parameters. So we'll get back to that later on. We do that by defining some measures of how well we align the data and how little we shift the data. Now there's slack and there's segment, but there's also the reference. We have to define what do I want to align towards. One option is that you can just pick a random sample, and that may work quite well. So let's say this is one chromatogram and this is another one. So I can pick any of those if I want. But imagine another sample looks like this. Now I have a third peak. So if I selected this one as a reference, then it's going to be very difficult to align all the subsequent samples that have a peak out here. So I really would like to have a representative sample, a sample that has all the peaks. Sometimes you can design one yourself. Very often people just use the mean chromatogram or the median. You can also take maybe the most average sample. So a sample that is representative of all the samples. If you're doing chromatography and you're measuring samples, sort of the first samples are measured initially and then you continue in time. So there's a time relation in your sample matrix. Then you may expect that the shifts are gradually getting worse and worse. So you wouldn't want to pick one of the first or one of the last samples because you expect that in the middle you'll be closer to the first samples and you'll be closer to the last samples. So you simplify your warping by taking one that's in the middle. Well, you need to know something about your data to sort of qualify which type of reference is useful for you. Okay, let's try and have a look at maybe not this particular data, but a more complex one. So let me open MATLAB and say load. This is a fairly big data set. It's not in PLS Toolbox, but it's 150 samples and there's 7,000 time points. Let's take a look at it. So it's a chromatographic data set. Those are ticks. So GCMS data that's been summed across the mask channel. And let's have a look and see if we have any kind of shifts. I'm gonna take a look at the, yeah, that's fine. I do not want points. Oh, and I want the rows. So I want the individual chromatograms, but I want all of them like this. Let me zoom in a little bit. Let's take a look. So you can see that there are definitely some shifts here. And it would be nice if we could align those. Let me take a look at this using the linear index instead of time in minutes. Then it's going to be easier for me to select a certain region of the data. Let's see. Now I want to select just a part of the data just in order to speed things up a little bit. And I don't want to have, let me show you what you don't want to do if you align. Let me see here. If I start my chromatogram right at the beginning of a peak, then the warping, the cow warping, will not have any flexibility in the beginning here, because I cannot move it very much. In reality, cow has most flexibility in the middle. And what that means is that if you have misalignment in the beginning of the signal, it's probably important that you have some baseline to the left of it. And some people will actually add a little bit of baseline to make the algorithm more flexible for the first or the last peaks. Well, I think I'm gonna say that we're gonna look at a region like, let's do something like this. Maybe I'm gonna start here. So around 2800, let me write that down. 2800, and how far should we go? Maybe we go here, 3500. Okay, I want to make a smaller data set. Like this. So that's only 700 variables. Let's take a look. Yeah, that looks nice. There's something fishy going on here. Some kind of gradient or something. I'm gonna disregard that for now. So let's open our analysis interface. You can actually just write analysis if you like, it doesn't really matter. Now it's gonna open up being PCA, but we're only interested in the pre-processing for now. Let's see, we'll take this one. And we will find the pre-processing. I'm not gonna do auto-scaling on this one. Okay. So the alignment. Oops. Stop. Here we are. Alignment. I would like to do cow. Now I have to choose the slack and the segment. So the segment is the length of the window. We have about 700 variables, and we have very little idea about what would work. So let's start with 100 and a slack of 5. Let's see what that does. We also have to select a target, but let's make life simple for now and just say auto. And let's see what happens. Well, definitely we got the big peak quite nicely aligned. We may also have overdone things a little bit. Maybe we changed the shape. If you look here, you can see that the peaks are fairly Gaussian, but that's not really the case here. So maybe this was a little bit too flexible. Let's have a look at the smaller peaks and see how well we did here. Oops. Well, we did a pretty good job there. I'm gonna try and make it a little bit less flexible. So I'm gonna lower the slack and I wanna increase the segment length, just to see if we can do equally well. Well, we don't do so well now. Let's see. Actually, it seems like we're hardly aligning at all. Let me see here. No. Okay. I'm gonna try and change the slack and see what that does. Seems to help quite a bit. What about the small ones here? Not perfect, but a little bit better, definitely. Not quite good, but definitely better than before. So maybe we lower this one a little bit. Yeah, it seems like this might be working, but maybe, yeah, now we run into the problem of the shape changes. So let me try and change the slack again. Let's see what that looks like. That's better, I think. Not perfect, but it's better. Normally, especially if you're doing chromatography, you do not want shape changes. You prefer misalignment to shape changes. But you can see that you may have to play around quite a bit with this in order to find a nice result. And another thing is that you may also find that it's easy to align the bigger peaks, because of course the bigger peaks, they define the correlation more than the smaller peaks, which means that you may actually want to do some kind of scaling before you do your alignment. This one doesn't look particularly helpful in this case, but that may help you focus on the smaller peaks, or you may split up your data in several parts and align them independently. Another trick that people sometimes do is also to do a very mild alignment, but then doing it several times. So rather than trying to find these settings for doing a nice alignment, you do a moderate alignment that definitely doesn't change your shape, and then you repeat that, or with some modifications, until you get a nice alignment. In the next video, we're going to try and see how we can automate this process a little bit to make it easier. Thank you.